All right, welcome back, everybody. I hope you're all doing well. Hope you all had a good break. Um, I recently finished grading all of your exams from before the break, so if you go on Gradescope, you should be able to see your grades and also my comments on your answers. As always, I would be happy to chat about your test in more detail if something was wrong and you're not sure why. Um, I also wrote out my own answers to the questions and put them on our class website, so you can check that out too if you just want to know what the answer should have been. That's another way you can do it. Um, I'm sure you've all heard about the recent decision to allow people to go pass-fail on your classes. The Yeah, please let me know if you want to know what your grade is for that purpose, or I suppose for whatever reason, you can let me know. We have 2 more weeks of ordinary class, so we are going to have a homework and a quiz this week, and a homework and a quiz next week, and then that'll do us. Then we have the final exam whenever it is. Anybody have any questions about that kind of business? Nope. All right, great. So yeah, please let me know if you want to talk about the test or if you want to talk about your grades. I'm into it.
I actually have a question about the final.
Yeah, sure.
Is that going to be like this? Is it going to be cumulative, like on everything we've learned?
So yes, but I want to give you all a chance to show me what you got on the new stuff too. So the stuff which we do this week and next week, 1/3 of the test will be on that new stuff, and then the rest will be on anything goes. So you should expect, if I made it sort of evenly throughout the whole semester, then a lot of the new stuff probably wouldn't make it onto the test. So you should expect the new stuff to be on there, plus some other questions about older stuff too.
Okay, thank you.
I'm going to have, one of the days next week we'll do just like an ordinary sort of test review. So I'll talk a lot more about that in the future. All right, great. So what we're talking about this week is the definite integral, and I just wanted to do some examples of the definite integral. I hope you can all see my screen. The definite integral. The integrals we've been talking about so far, the antiderivative is called the indefinite integral. The definite integral is something actually completely different. There is a deep relationship between the two, but we haven't talked about that yet. As far as what we're doing this week, the definite integral is totally different from the indefinite integral. The indefinite integral is the antiderivative, and the answer you get is a function, like with a plus c on it. The definite integral is actually a number. For example, if I have the definite integral, say, -1 to 3 of x squared dx, it looks like an indefinite integral, only it has those little numbers, the -1 and the 3, right? Those, if you see those, it means it's a definite integral, and what it represents is, like I said, totally different from the indefinite integral. It represents like this function, x squared inside there. So you look at the graph of that function, and then you measure the area under the curve from -1 over to 3. This area and this area over here. So this is this area here and here, right? All that area together. The black shaded area. All right, this is called the definite integral. It is a number. Why is it called an integral if it's so different from the antiderivative? And there is a relationship. We'll talk about that next week. Today's problems, all the problems from this week, are about estimating that area. That area turns out to be very important in the real world. I'm not going to talk about that today, but estimating this area. You know, it's a weird curvy shape, so generally, like, there's no obvious way how to find the true area because it's a weird curvy shape. But there are several different strategies for estimating that area. And the most basic one is you, instead of considering this curvy area, you break the area into a bunch of sort of vertical strips, and then you make each of these vertical things into a little rectangle. And these rectangles, they're pretty close to the shaded black area, but the rectangles, their areas are easy to find, right? You don't know the true curvy region's area because it's a weird curvy shape, but the rectangles, you can always find the area of a rectangle, right? So the strategy is you break the curved region into rectangles, and then add up their areas. And those areas, the rectangle areas, are easy to do. All right, each rectangle area is, of course, the base times the height, and we have sort of names for the base and the height. Here I drew rectangles. It's kind of hard to see my picture. Let me just draw again. You make a bunch of little rectangles like this, and you make them so that they all have the same width on the base, but they all have different heights. Each rectangle area, this width here, I'm going to call delta x. Sorry, I'm drawing a picture under my beautiful face. Each rectangle, we draw them so that they all have the same base width, and they all have different heights. So each rectangle area is delta x, which is the width, times f of something, I will say. This is the height. Why is it f of something? It's because these heights would be these vertical distances, and they those heights are determined by where the curve is, right? The graph of the function. So the actual vertical height of each of those things is obtained by just plugging some number into the function, and it's going to be a different number each time. Each of those different points gives you a different number to plug into the function, all right? And then we add this all up. Okay, this is the idea. Let's just do some examples. I don't know if this sounds complicated maybe, but actually when you're doing particular examples, it's not really complicated at all. You just have to remember how to do it. Let's try. So I really just have 2 examples for us to do today. Ooh. Number 1, let's estimate the integral from 1 to 5 of x squared minus x dx using, I'm going to say n equals 4, and I'll say, sorry, I'm going to do n equals 8. It'll be even better. And I will tell you, I got parts, part A, B, C, D, E. Can you believe it? A. Part A is going to be the left endpoints, and I'll say what this means. I mean, you saw it in the video. Part B is going to be the right endpoints. Part C is going to be the midpoints. Part D is going to be the trapezoid rule. For the trapezoid rule, you don't use rectangles, you use little trapezoids. And part E is going to be Simpsons rule, which is yet another variation on the shapes that you use. Instead of rectangles or trapezoid, for Simpsons rule you use a strange sort of rectangular shape with a parabola on top. We'll get to that when we get to it. Let's get going with this. So part A, using the left endpoints. The way you want to do each of these is, the answers are going to be pretty similar for all of these parts. But all of them, first of all, are based on dividing up the interval into pieces. Somebody have a question? Thought I heard something. Nope. divide up the interval into a bunch of pieces. Now this problem is about the area from 1 to 5. So the fact that I have this 1 and 5 right here, that means I'm considering the region of x values starting from 1 going up to 5. So I'm going to just make a little diagram of that portion of the x-axis. Using n equals 8, that means I need to divide this up into 8 pieces. Well, I can do that by dividing it in half first, and then in half again, and then in half again, right? I have made the division into 8 pieces. And the first thing we need to do is figure out where those values actually are. Like, where is the value in between? When I cut it in half, I think that would be 3, right? The number in, like, right in the middle between 1 and 5 would be 3. And then in between 1 and 3 would be 2, so that's a 2, that's a 4. I'm trying to label these points just sort of by common sense. And then I have in between 1 and 2 would be 1.5. 2.5 is here, this is 3.5, this is 4.5. All right, so first step is sort of write down just a very basic diagram of the x values you're talking about, divide it up into the appropriate number of pieces, which in this case is 8 pieces, and then figure out, you know, what all those values are. This you can usually do by some kind of common sense. If for some reason the common sense is failing you, then you can always remember a formula for delta x. It is b minus a over n, where b and a are the two endpoints, the 1 and the 5 in this case. So in this example, it would say 5 minus 1 over 8, n is 8, which is 4 over 8, which is 1/2. That's the width of each of these little things, right? Isn't that nice? So this is one way that you can figure out where those little points are if for some reason you can't just figure it out by common sense. You can find the delta x using that little b minus a over n, and then that'll tell you where those other points go. All right, anyway, in this part A, we are using, I said, use the left-hand endpoints. That means I'm going to choose, for each of these little regions, I'm choosing the point on the left. All right, I just circled the left endpoint of each of the small intervals there, each of the babies has 2 ends. I choose the one on the left. All right, and my answer then is obtained by plugging those points into the function and multiplying by delta x. So the integral from 1 to 5 of, with this function, x squared minus x dx is approximately equal to, what I said, I'm going to add together all of these things. Each time I multiply delta x times f of whatever the number is. So I get delta x, which is 1/2, times f of 1 is the first one. And then delta x, which is 1/2, times f of 1.5, which is the next number. 1/2 f of 2, which is the next number. I'm taking all of these red chosen values and plugging them into the function one after another. Every time I multiply times 1/2, because that's the width of each rectangle. These f of whatevers are the heights. All right. Put the dots. If you don't want to write them all down, that's totally fine with me. Put the dots. If you put the dots, you should write a few things at the beginning so I know what the pattern is, and then write the last one so I know where it stops. In this case, I stop with f of 4.5. That is the final leftmost endpoint of the intervals. All right. Now this right here, often I will write them. I will factor out the delta x, right? Here I have many things added together and they all have a 1/2 in front. So this is the same as 1/2 times all this stuff, right? F of 1, f of 1.5, etc. down to f of 4.5. And this is almost my final answer, but you shouldn't leave your answer like that with the f in it, because I will want to see that you know what the f means. What does the f mean? The f is this function in here, x squared minus x. So my final answer, this is going to look a little messy, but I do f of 1 is 1 squared minus 1, and then plus f of 1.5 is 1.5 squared minus 1.5, plus blah, 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 all the way down to the last one, f of 4.5 is 4.5 squared minus 4.5. And this is my final answer. If you want to, you can type all of that into your calculator. It's a real pain because there's a lot of stuff there inside the dots. On a test or a quiz, I would expect you to leave your answer like that. Any thoughts about this one? What are your questions? And I take a sip of my beverage here. What do you think?
So for part of the answers, when you were transferring steps, like what you just did from the where you wrote the integral to the next step down,
Yeah.
you left out some of the parentheses like before the f. Is that like, was that in place of like where the 1/2 would be now? I know it's a little bit of an abstract question, but I just noticed it in the video.
So like why there are parentheses here and here. That's because this 1/2 needs to distribute to make it the same as that.
Yeah, I just think, actually, you don't know. This is a question I'll have to ask you later because I have to find the example. Sorry about that.
Okay. Yeah, maybe one, I'm not sure if this is what you were thinking, but you could, if you want to, I'll do this sort of in blue. You may have thought there should be parentheses like this, where I just plug each of these things in, and they should still go together. That it would not be wrong to put parentheses, like those blue parentheses are correct. They're just not necessary in this example because I think
that's what it was, yeah.
Yeah. You don't need them here because all I have on the inside, like all of this stuff, is just all being added together. And you don't need parentheses when you're just, like if you're just adding, say, 1 plus 3 plus 5 plus 7. This is the same. If you put these parentheses or not, it's the same answer either way.
Okay.
When it's all added. The only time parentheses matter a lot is when you're mixing up additions and multiplications. Then it matters. But here they're all additions, so in this particular example, those parentheses don't matter.
Okay, awesome. Thank you.
Yep. Okay, great. So that was the part A. This was using the left endpoints. Part B is do all the same stuff, but using the right endpoints. So I'm going to use the same interval and everything this time. 1, 1.5, 2, 2.5. The only difference will be I use the right endpoints instead of the left endpoints. What's that? That would be these guys. Those are the right-hand endpoints rather than the left-hand endpoints. All right? And you can really just sort of, especially once you've done the other part, you can really just kind of jump all the way to the answer from this point. It's the same as what I wrote before, only you don't start with 1. You start with 1.5, and you don't end with 4.5. You end with 5. So I'm going to write the same stuff as before, but I begin with 1.5, so it's 1.5 squared minus 1.5. And then I got 2 is the next one, right? 2 squared minus 2, etc. And we end up at the end, which is 5. 5 squared minus 5. All right? This is using the right endpoints. It's all the same stuff. It's just a matter of which points you're using on the inside there. Any questions about that one? All right, great. Next part is the midpoints. Part C. Midpoints. Well, for that one, you're going to use the points that are actually right in the middle of those intervals. So I still have the same thing from 1 to 5. So this is 1.5, 2, 2.5, 3. What? Sorry, I didn't make enough little guys. 2.5 here, 3, 3.5, 4, 4.5, and then 5, right? And we choose the middle points. So you have to figure out what are the points right in the middle of each of these. These are the points that I'm concerned with now when I'm using the midpoints. And what are the midpoints? Like, can anybody say what's that first one on the left there? The leftmost red point there?
1.25.
1.25, yeah, that's in between 1 and 1.5. All right, and the next one will be 1.75, and then 2.25, etc. Right? This last one will be 4.75. Those are the midpoints. And when I do the approximation using the midpoints, it's just the same as the other stuff. So the answer using the midpoints is 1.25 squared minus 1.25 plus the next one, 1.75 squared minus 1.75. And then the last one is 4.75 squared minus 4.75. That's it. This is using the midpoints. All right. Any thoughts about that one? When it's the midpoints, you don't skip any of them. You use all of them in the same way as the others. All right. Okay, the other two are trapezoid rule and Simpsons rule. So for those, they are, again, similar. You use the same divisions of the points, but they have weird formulas, very slightly weird formulas, not really very weird at all. The trapezoid rule. And for these, you just need to remember the formulas. The idea of the trapezoid rule is, instead of using rectangles, you use trapezoidal shapes, which are like here. Rather than making a rectangle, I connect it with a straight line on the top. Then the area of the trapezoidal shape is very close to the area under the curve. So it's a better approximation than just making rectangles. Anyway, the trapezoid rule formula, let's see if I can put it over here, is this. You get b minus a over n on the outside. This is also known as delta x, right? So it's really, it's the same as this delta x that we saw on the outside in the previous examples. But then, on the inside, the only difference is this right here. You add together all the function values, except you put a 1/2 in front of the first one, and a 1/2 in front of the last one. This is the formula for the trapezoid rule. The important parts are these 1/2s. That's really the only difference between the trapezoid rule and what we were doing in the previous steps using rectangles. You are still going to put delta x on the outside. You are still going to be adding together a bunch of stuff on the inside. It's just you use all the points. You put a 1/2 on the first one and a 1/2 on the last one. That's all you do for the trapezoid rule. So, as to what does this formula have to do with the trapezoids? Well, it's a little complicated. I explained it all in the video, but for now, let's just talk about how to do it. So, I'm going to do, in my example here, delta x is 1/2. You could just put 1/2 on the outside, or you could write down, where that came from. It was 5 minus 1 over 8, right? That's the b minus a over n. And then, inside the parentheses, I have 1/2, because that's part of the trapezoid rule formula, and then I plug in the first x value. That's what this f of x0 means. It means the first x value. This is the next one, etc. This is the last one. This is the second to last one. Let's do it. F of x0, the first value was a 1. So I get 1 squared minus 1, right? And then plus 1.5 squared minus 1.5 plus 2 squared minus 2 plus, etc. Right? I'm using the same old points, plugging them in, dot, dot, dot. The second to last one I'll write 4 is 4.5, right? 4.5 squared minus 4.5, that's the second to last one. And then the very last one needs a 1/2 in front of it. 5 squared minus 5. This is my answer using the trapezoid rule. You'll notice I did put some parentheses in there. Those parentheses are necessary because they have those coefficients of 1/2 in front of them. All right. Any thoughts about that one? Of course, you can plug all of this into your calculator. It should give you a number. I'm not going to do it because it's a pain, but on a test or something, I would expect you to just leave it like I just did. All right. Okay, one more, and that is Simpsons rule, part E, Simpsons rule. And this, again, has a slightly weird formula to plug into. On the front, instead of b minus a over n, it is b minus a over 3n. And then on the inside, you have to remember how the coefficients goes. So Simpsons rule coefficients go like this: f of x0 plus 4 f of x1 plus 2 f of x2 plus ... And inside here, the coefficient alternates: 4, then 2, then 4, then 2, etc. All right. This is a kind of a weird formula. This it's complicated where this formula comes from, but for now, I'm just going to say this is the Simpsons rule formula. You end up with the second to last number will have a 4 on it, and then the very last one is f of xn, like so. All right. The second to last value will always end up with a 4. It does this alternation: 4, then 2, then 4, then 2. It always ends up with a 4, and that's because n, in order to do Simpsons rule, n must be even. So you only do Simpsons rule when n is even, and in that case, you're always going to have a 4 at the end in the second to last term. All right. That's the equation for Simpsons rule. How you use it, you just plug in. So in this particular problem, I go b minus a over n is 5 minus 1 over 3n, will be 3 times 8. And then inside my parentheses, I am plugging in all the values. F of x0 means the leftmost point is 1, so this is 1 squared minus 1. Plus, and then 4 times 1.5 squared minus 1.5. Plus 2 times 2 squared minus 2. Plus, etc. Alternating 4s and 2s. Finally ending up with 4 times the second to last point was 4.5. 4.5 squared minus 4.5. And then the very last point has no coefficient. 5 squared minus 5. And this is the answer using Simpsons rule. Simpsons rule, as far as approximations goes, Simpsons rule is the most accurate out of any of these. And so if you're doing this, when people do this in the real world, which they do, actually Simpsons rule is used all the time in the real world. Simpsons rule is the one that people use in the real world because it's more accurate than the others. It's a little more complicated, the formula, but in the real world, when people do this, they're using computers anyway, so it doesn't really matter. Using a more complicated formula, the computer's going to do it for you. All right. Any questions about that one? That was the Simpsons rule. All right, I got one more, one more example to do of all of these, and I think that'll do it for what I wanted to talk about. So, one more example. Let's try the integral from, let's do 6 to 9 of x squared ln of x dx. All right. Don't get any heart palpitations about the ln. I know the ln makes some people nervous. It really doesn't matter. You'll see what exactly the function in there is. It plays almost no role. I mean, you have to write down the function, but how complicated it is or anything like that, it doesn't matter. Because this problem, I hope you've noticed, has nothing to do with the derivative or the antiderivative of anything. You don't have to do anything to the function. You just have to sort of write it down. So no problem. And I'm going to say using n equals 6, and then let's just do the same, A through E parts. All right? I'll refresh your memory of what they were. So part A is the left endpoints. We should, as usual, make this simple little chart of the values. Now this time we have to go from 6 to 9, and I divide this region into 6 equal pieces. That means divide it in half once and then go thirds on each of the halves. That's how I would do it. And we have to figure out where those numbers are. Like what, specifically, what are those little numbers? Like I said before, if usually I would just sort of say by common sense you can figure this out. If you don't like common sense, or for some reason it's not coming together for you, you can always remember delta x is b minus a over n, right? Which in this example would be, the b and the a are the 6 and the 9. So this would be 9 minus 6 over n is 6. That would be 3 over 6, which is a half. So apparently the delta x is a half, which means this little width here is a half, which means that must be 6.5, and then this must be 7, and then 7.5, and then 8, then 8.5, and then 9. So it all works out. This is how you can figure it out if for some reason the common sense isn't coming together for you. All right. This is my little interval of x values, and for this part I'm using the left endpoints, which is this one, this one, this one, this one, this one, this one. All right. And I think I'm ready to write my answer. I put the delta x outside. Once you know what you're doing, you can jump all the way to the final answer, and that's totally fine with me. First thing on the inside, the inside will be a bunch of stuff added together. First thing is plugging in 6 to the function. It becomes 6 squared ln of 6. And then I go plus 6.5 squared ln 6.5 plus blah, 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 etc. The last one will be 8.5 squared ln 8.5. And that's it. All right? You can put it in your calculator if you want. I do not want. All right. And I hope you agree with me. This is what I meant before when I said don't worry about the ln. It doesn't really matter what the function is. I mean, I had to write the ln, but I didn't actually have to do anything to it. So no matter what the function is inside the integral, you can always do this because it requires no funny business with the function. Any questions about that one? All right, let's see if we can do the others. That was the left endpoints. Let's do the right endpoints. It's almost the same. Can somebody tell me what's the difference when I use the right endpoints?
Well, you're going to be shifting one over to so you're going to be using 9 now instead of 8.5.
Yes, the last one will be 9, and the other difference?
Starting with 6.5.
Right, we begin at 6.5, so we do not include the 6, but we do include the 9. That's the only difference. So I hope you don't mind, I'll just write the answer. It's 6.5 first, 6.5 squared ln 6.5, plus 7 squared ln 7, etc., all the way up to 9 squared ln 9. That's the answer using the right endpoints. Excellent. How about the midpoints? Now this one you have to do a little figuring. The midpoints would be right in the middles. Here, right? These guys, these blue guys. Those are the midpoints. And what are they? It's not so hard. The first one there is 6.25, right? And then 6.75. So could I just write the answer for the midpoints? I hope you won't mind. The midpoints. Again, you have the 1/2 on the outside. This time I start with 6.25 squared ln 6.25, right? Plus, next one is 6.75 squared ln 6.75 plus, and so on. Then the last one will be 8.75. All right, that's how we do with the midpoints. They all look kind of the same. It's just a matter of exactly which points you're plugging in. All right. Remember, all of these are supposed to be approximations of the true curved area. So if you were to plug these into your calculator, you would see the answers, like these 3 parts here, the answers would be not the same, but they would be close together, right? Similar, because they all represent 3 different approximations of the same true curvy area. Okay, how about trapezoid? All right, now this one you have to use a formula. But remember the formula had b minus a over n on the outside, so that's going to be, forgotten already, b minus a over n, 9 and 6. It's the same as the delta x, but it's 9 minus 6 over 6, right? And then inside of the trapezoid rule, you use all the points, you add them all together, but you put a half on the first and a half on the last. So it's going to look like 1/2 and then 6 squared ln 6 plus 6.5 squared ln 6.5 gets no coefficient, 7 squared ln 7, etc. The second to last one is 8.5 squared ln 8.5. And the very last one is 1/2 9 squared ln 9. All right, this is the trapezoid rule. Any thoughts about that one? All right, and then finally, the Simpsons rule is again similar. You just have to remember the specific format of the formula for Simpsons rule. It says b minus a over 3n, so there's an extra 3 in this denominator outside. And then the other thing is, in Simpsons rule, on the inside, you use all the points. The first one has no coefficient. The next one has a 4, so 4 times 6.5 squared ln 6.5. Then a 2, 2 times 7 squared ln 7. Then alternating 4s and 2s. The second to last one has a 4, 4 times 8.5 squared ln 8.5. And then the very last one has no coefficient. Nine squared ln 9. Like that. This is the answer using Simpsons rule. All right. Any questions about that? All right. I think that's about all I wanted to say for today. We got about 10 minutes left, but I don't think I need to do another example for everybody. I am going to have my office hours starting now and until 2. So I guess, if you do have questions, hang around and we'll talk about them. Otherwise, I will see you all back here tomorrow.